In this part of video, I'm going to discuss about the power in an ideal transformer. Some of the question was raised by some student regarding the primary voltage and secondary voltage and E1 and E2 that I will also explain here, and then I will explain how the power of an ideal transformer, real power and active power and reactive power both are same. Either we see in primary side or in secondary side. So let us see here. This is our transformer. This is magnetic core of the transformer. Drawing here like this. And this is our primary side. And this is our secondary side. So here it is V2. This portion where we connect the load. This is voltage V2. And here it is E2. Here it is E1 induced voltage. And here it is supply voltage V1. So someone was asking that why V1 is equal to E1. So the simple answer is that there is a no resistance for an ideal transformer. So there is a no drop in this part of the transformer. So whatever voltage we are giving here is same as E1 induced here. Also, if we connect load here, the resistance of this winding of the transformer is 0 for ideal transformer. So E2 will be also equal to V2, and if load is not connected, V2 is by default equal to E2. Now, this relation we have already derived and written V1 by V2 equal to E1 by E2 equal to I2 by I1 equal to N1 by N2, and this N1 by N2 is called A turn ratio of the transformer. So this relation, I told you, it is a very important relation for all type of transformer application for primary to secondary and secondary to primary. We will see how we will transfer this secondary voltage into primary voltage and primary voltage into secondary voltage. And if here load is connected, here current primary is I1 and here secondary current is I2. So how we can transfer this load current in the secondary to the primary side, and how we can transfer the primary current into the secondary side. This I will have also to study and to look these equations in a detail. Now, you see, for an ideal transformer case, this is the input power, and power, you know that power is voltage multiplied by current and cos theta. This is power input at the primary side, and theta 1 is the angle between voltage and current, and this cos theta is called power factor. So this power is the real power or active power. Same way, P output equal to V2 I2 cos theta 2, power output to the load at the secondary side. This is secondary side and this is primary side. So since voltage and currents angle are unaffected by an ideal transformer, so current and voltage will not be affected in ideal transformer. So this angle theta 1 and theta 2 is equal to theta. Now this relation is, we have to see that input power is equal to the output power. So this relation you see here in V2, if I am going to write this relation V1 by V2, it is equal to N1 by N2, and N1 by N2 is nothing but it is A. This is N1 by N2. So V1 by V2. So from here, V2 goes here and V1 and A come here. So you will get V2 equal to V1 divided by A. So V1 divided by A, that is why it is written here V2. And similarly, the relation I2 by I1 equal to N1 by N2, that is A. N1 by N2, that is turn ratio A. So from here, We can also get the value of I2, that is A multiplied by I1, that is written here. So what we do, this I2 value is put in here, and V2 value also put it here. So in P output equation, this equation, V1 by A, V2 is V1 by A, and I2 is A multiplied by I1, and cos theta 2 is cos theta. So this A and A will cancel out. So V1 multiplied by I1 into cos theta. This is nothing but this is input power. So this P in means P output equal to P input for an ideal transformer. The output power of an ideal transformer is equal to its input power. Now I am going to see the same relation for reactive power. So reactive power, you can also very easily verify this relation. Q input equal to V1 I1 sine theta 1, and output Q you will be V2 I2 sine theta 2. So very easily you can put the value here. V2, that is V2 is equal to V1 by A, and I2 is nothing but A multiplied by I1, and this will be equal to sine theta. So A will be cancelled out, and it will be also equal to V1 I1 sine theta. So this V1 I1 sine theta is nothing but Q input. So Q reactive power input and reactive power output for an ideal transformer both are same. Here I want to draw one more diagram. You see here, for an ideal transformer, I have told you this is your windings on the primary, and this is the winding on the secondary. And this portion is called core, and here our input side is V1, V1, and this output side load voltage is V2. V2 is the secondary voltage. N2 is the secondary number of turn, and N1 is primary number of turn, and I1 is primary current, I2 is secondary current. So this, when this transformer, suppose secondary is not loaded. Not loaded means I2 is 0. I2 is not there. Secondary current is not there. So your diagram will be like this. Secondary is not there. So this diagram will be like this. Here I2 is 0, means it is open circuited in the secondary side, and in the primary side this current I1 is coming and going and coming, returning. So this I1 current, when secondary is open, is called excitation current. When secondary is open, the current taken by primary is called excitation current. Is called excitation current. Is called excitation current. But when secondary is loaded, at this time the excitation current is very, very small. That current is, excitation current is denoted by I naught, and then this I1 is equal to I naught, excitation current. But once this secondary side is loaded, means secondary current, in the example here, secondary is going to flow in the secondary side. At this time, this I1 will not be equal to I naught. At this time, the current I1 becomes equal to I naught plus one extra current, that is called I2 prime. or I2 dash. It is not equal to I2. I2 is flowing current in the secondary side, but this current when seen from the primary side, its value is represented by I2 dash, that I will see it in next slides. What is the effect of how much I2 is there, I2 dash in the primary side, that we will see in later part. But it is not equal to I2. You keep in mind that I2 current is the secondary current, but I2 dash is the current referred to the primary side, I2 dash. So now I1 has to give this extra current, and I0 is the excitation current. So this extra current has to come from the I1. So now this I1 will be equal to I0 plus I2 dash. This I0 in fact also has two components that we will see later. One component is called IW and another component is called I mu. That is called magnetization component. Actually, this I0 is the uh, current, excitation current, which has two components, I W and I mu, magnetization component. So this I0 is very small. This I0 value, this I0 is 2 to 5% of full load current, of full load current. What does it mean? Suppose if your secondary current, this current is full load current is 100 ampere. So this I0 will be 2 to 5 ampere. 2 to 5% means 2 to 5 ampere will be the no load current. If this full load current is 100 ampere, then their excitation current will be 2 to 5 ampere. Suppose if it is 2 ampere, then from here, this magnetization component is about 95 to 98% of this I0. This my I mu is magnetization component of I0 is 95 to 98%. And the remaining 2%, 2 to 5%, this component that is called, this is called iron loss component. This is called iron loss component, that I will explain you later what is iron loss component. So this component is actually iron loss component, and it is very small, and this part is the very big part of this I0 excitation current. That is why it is called magnetization component. And this component in fact is needed to magnetize the core of the transformer. If the core of the transformer is not magnetized, then the flow of energy from primary to secondary will not take place. So magnetization of core is highly required. So I was discussing about the ideal transformer and magnetization component of the transformer. Now I told you how we can transfer secondary side parameter to the primary side, maybe current, maybe voltage, maybe impedance to the primary, and from primary to secondary how we can transfer. So this topic is for impedance transformation. This is the very important topic, and once you understand this thing, so you will be able to understand all the things of the transformer. So now you see here in secondary side the voltage is V2 and current is I2 and impedance is Z2, secondary side impedance. So impedance we can write from the Ohm's law, V2 by I2. This is secondary voltage and this is secondary current. So impedance will be Z2 equal to V2 by I2. Now similarly we can also write impedance in the primary side will be equal to V1 by I1 written here. So this again we have to use the same relation, V1 by V2, V1 by V2 equal to N1 by N2 and this n1 by n2 is nothing but it is A, turn ratio of the transformer. So for V1, we can write V1 is V2 multiplied by A. So here it is, in place of V1, it is written A multiplied by V2. Similarly, I have to change I1 also. So I'm going to write here I1 divided by I2, which is equal to N2 by N1. N2 by N1, and N2 by N1 is 1 by A. N2 by N1 is 1 by A. N1 by N2 is A, so N2 by N1 will be equal to 1 by A. So from here you can write the value of I1 equal to I2 by A. That is why it is written here, I2 by A. So after simplification, A go upside, so it will be A square multiplied by V2 by I2, and V2 by I2 is Z square. So you see here, very interesting relation. This is the secondary impedance multiplied by A square, and A is N1 by N2, which is equal to primary impedance. It means when this impedance Z2 is seen from primary side, its value will be equal to this Z1, this A square multiplied by Z2, this is called Z2 dash, and Z2 dash is read as secondary impedance referred to primary side. This Z2 dash is called Z2 dash is called Z2 dash, which is equal to A square multiplied by Z2. This is called secondary impedance referred to primary side. Secondary impedance referred to primary side. Referred to primary. Getting point? Primary. Means ki secondary impedance Z2 is, suppose if it is Z2 is 100 ampere and A is 10. It is, suppose it is 100 ampere Z2 and A is 10. So 100 multiplied by 10 square. So if you see this impedance in the secondary side, so it will be 10,000 ohm. But in the secondary side, it is 100 ohm. So this thing, this circuit diagram is now represented like this. I1 is flowing here, same. And this impedance is referred to the primary side, and it is written as Z2 dash, which is secondary impedance referred to the primary side. So you here we need to consider every time that which side we are considering the values, primary or secondary. So accordingly we have to change the notations and the calculations also. So you see here this relation, whatever in the primary side impedance is given as Z1 equal to A square, Z2, this is called Z2 dash, already derived. An impedance Z2 connected in secondary will appear as an impedance Z2 dash looking from primary side. This is looking from primary side. This is called secondary impedance referred to primary side. Impedance can be transferred from secondary to primary if its value is multiplied by a square of term ratio. A square of term ratio. An impedance can be transferred to the secondary side in the similar way. If primary impedance, then it is called Z1 dash, and it is 1 by a square z1. So you can verify this result as early I have done for z2 dash. You can also get this relation as z1 dash. So this is the impedance referred to secondary side. So if you go into the secondary side, you have to divide it by the square of the turn ratio, because here we are multiplying it by the turn ratio, and here you have to divide it by the turn ratio. So this is the some concept that I have given here. Next time I will give you next thing.